The Hessian matrix tells us how a function curves at each point. Imagine walking on 3 different paths: a happy valley, a sad mountain, and a strange saddle path. Their curvatures are fundamentally different. Let's examine 3 fundamental curvature types. First, the convex bowl, it smiles at us from all directions. Second, the concave frown, it curves downward everywhere. Third, the saddle, smiling in one direction while frowning in another. The Hessian matrix captures these curvatures mathematically. For a 2D function, it contains 4 second derivatives: how the slope changes in the x direction, y direction, and their interactions. The eigenvalues of the Hessian reveal the curvature secrets. 2 positive eigenvalues mean convexity, like our green bowl. 1 positive and 1 negative creates a saddle. 2 negatives make a concave shape. Let's see examples. Now the practical use. Newton's optimization method uses the Hessian to make perfectly calculated jumps. Watch how it reaches the minimum in one step, while gradient descent takes many small steps. The Jacobian matrix is the multidimensional generalization of the gradient. While the gradient works for scalar functions, the Jacobian handles vector-valued functions, mapping how each output component changes with each input variable. First, let's recall the gradient. For a scalar function like f, x, y equals x squared plus y squared, the gradient is just a vector of partial derivatives. But what if we have multiple outputs? For vector functions, we need a matrix where each row is the gradient of one component function. This is the Jacobian. It contains all first-order partial derivatives of the vector function. Geometrically, the Jacobian describes how the function locally stretches and rotates space. Its determinant gives the local scaling factor of the transformation. In deep learning, the Jacobian is crucial for models with multiple outputs. Some advanced generative models use the Jacobian to enforce constraints or compute more sophisticated updates than standard backpropagation. The Taylor series is one of the most powerful tools in mathematics. It lets us approximate complicated functions using simple polynomials. This becomes crucial in optimization, where we often need to approximate functions around specific points to understand their behavior. The core idea is simple. At any smooth point, a function can be represented as an infinite sum of polynomials, with each term carrying more information about the function's shape. The first term gives the value, the second the slope, the third the curvature, and so on. Let's see how adding more terms improves our approximation. We'll start with just the constant term, then add the linear term, then quadratic, and so on. Watch how the polynomial gradually hugs the curve. The general formula for the Taylor series around pointer sums over all derivatives, each multiplied by xa raised to the corresponding power and divided by factorial. This gives us a perfect local approximation that becomes exact with infinitely many terms. In optimization, we often use second-order Taylor approximations. The gradient gives us the linear term, while the Hessian provides the quadratic term. This helps algorithms like Newton's method make better decisions about where to move next. The quality of Taylor approximation determines how optimization algorithms converge. First-order methods use linear approximations and converge linearly. Second-order methods use quadratic approximations and can converge quadratically, much faster when near the optimum. In optimization, convexity is the golden property that guarantees our algorithms will find the global minimum. A convex function has no tricky local minima, just one clear bottom point that we can reliably reach. Let's see what makes functions convex. Visually, a function is convex if the line segment between any 2 points on its graph lies entirely above the graph. Let's compare convex and non-convex shapes. Formally, a function f is convex if for any 2 points x and y, and any alpha between 0 and 1, the function value at the weighted average is less than or equal to the weighted average of k function values. This is called Jensen's inequality. In optimization, convexity guarantees that any local minimum is also global. For convex problems, gradient descent will always find the true optimal solution. Let's compare optimization on convex versus non-convex landscapes. How can we test if a function is convex? For twice differentiable functions, we check if the Hessian matrix is positive semi-definite everywhere. This means all its eigenvalues are non-negative at every point. We've explored 4 fundamental concepts in mathematical optimization. The Taylor series gives us local approximations. The Jacobian handles multidimensional transformations. The Hessian reveals curvature information. And convexity provides global guarantees. Together, they form the mathematical foundation for modern optimization algorithms. These mathematical tools power optimization algorithms. Gradient descent uses first-order Taylor approximations, while Newton's method leverages second-order terms through the Hessian. The Jacobian enables optimization in multi-output systems. And convexity theory tells us when solutions are globally optimal. In modern machine learning, these concepts appear everywhere. Neural networks use Jacobians for backpropagation. Convex relaxations help solve non-convex problems. And second-order methods accelerate optimization. Understanding these foundations helps us develop better algorithms and understand their limitations. To summarize, Taylor series provide local approximations. Jacobians handle multidimensional mappings. Hessians reveal curvature. And convexity gives global guarantees. Mastering these concepts gives you powerful tools to understand and improve optimization algorithms in machine learning and beyond.